Our project is based on an autonomous framework by combining the latest research and developments into mapping and navigation into one repository. By making use of the ClearPath Robotics Husky, the Husky++ is implemented by using three-dimensional autonomous mobile navigation by the addition of extra sensors and traversability algorithms. This repository can then be downloaded and installed onto any robot equipped for rough terrain, uplifting its software to traverse its environment. The Husky++ was initially designed with the purpose of search and rescue in mind, with the need for a remotely operated, unmanned ground vehicle to explore and traverse harsh and hazardous environments. However, due to our project being designed for a remote operator to monitor the robot at a safe location, the domain applications can be extended for things such as agriculture, nuclear decommissioning, mining, and self-driving.
The Husky robot came with a powerful two-dimensional outdoor LiDAR. In order for the robot to be able to get a three-dimensional point cloud of its environment, we rotated the LiDAR to sense along a vertical plane. The rotated LiDAR is then mounted on top of a motorized rotation stage. We position the LiDAR mount at the front of the robot's top plate. Two stepper motors differentially drive the rotation stage to maintain a fully controlled, smooth, 180-degree continuous pan of the robot's environment. Gears are used to ensure the stepper motors have enough torque to turn the LiDAR. Inside the LiDAR mount is a joint limiter bracket. This prevents the LiDAR rotating further than 180 degrees. Current sensors embedded within the motor controller are able to sense these limits. To achieve this final design for the LiDAR mount, we experimented with multiple design iterations.
We used a stereoscopic camera which produces a depth map with the range of up to 20 meters. The depth camera was simulated using a gazebo plugin which can stream the camera feed and depth map to Arvis. To control the position of the camera, we mounted it on a pan tilt unit with a pan range of 5.2 radians and a pitch range of 1 radian. The pan tilt unit can be controlled remotely using a joystick or keyboard control, allowing for closer inspection of points of interest by the operator.
To represent the additional sensors, we remodeled the Husky description URDF to include the IMU, GPS, LiDAR, and stereoscopic camera. To virtually simulate the sensor data, we use gazebo sensor plugins. Using sensor fusion, the robot fuses sensor information from the wheel encoders, GPS, and inertial measurement unit using an extended Kalman filter. This, in turn with the LiDAR and camera sensor data, improves the accuracy of mapping, navigation, and localization.
To ensure the safety of the Husky and those around it, manual control can be remotely taken to override the existing directional controls from its pre-planned control panel. For control via a remote computer, a LAN network has been set up. A device on the network functions as a server by distributing static IPs to all of the devices on the network, including the Husky, and also functions as a reference point for time synchronization. A 5G antenna has also been attached to the Husky to allow high-speed communication over long distances.
We used a ROS package called Octomap. This package takes the individual laser scans as well as their respective recording locations and merges them to generate a three-dimensional view of the robot's environment. The generated map is then filtered and geometric features such as normals and surface curvatures are computed. Point cloud segmentation is then performed and point clusters are labelled according to the geometric constraints applied to the surface normal directions, mean curvatures, and three-dimensional point coordinates. This allows us to analyse the environment to identify regions such as walls, terrain, stairs, ramps, and other obstacles.
Traversability is then computed as a cost function, which takes the point cloud classification, obstacle clearance, terrain roughness, and point cloud density into account. Path planning can be performed in two ways, by either drawing your desired path directly in HardViz, or by setting a waypoint and allowing the robot to plot its own path. When the robot uses a waypoint system, a global planner looks for a traversable path by examining the terrain analysis. Then, a local path planner drives the robot along the global path continuously with plotting its path to account for dynamic environment change. To determine the path, a randomized A-star sampling-based approach is used to capture the connectivity of the traversable terrain.
We designed this project to be open source by using one GitHub repository to contain all associated files and documentation. Complementary guides show the installation methods and required dependencies. Someone wishing to replicate and further progress the project can follow the conclusive README files to easily download, install, and run the code, allowing for easy reproducibility.